Well, good afternoon. Hopefully, we'll try to keep you awake here. I know it's a little bit later in the afternoon. Lunch is kicking in. What I'd like to try to do is give you a little bit of a different perspective. So you heard, very detailed presentation on what's being done to actually improve the overall efficiencies of solar cells. Well, I'm going to really try to take it from the end user or the utility perspective, really trying to show you, as we start to deploy more and more of these renewable technologies, some of the challenges that we as a utility have. And it's very different. I think what you should see here is that we have this reliability, we have these goals, and in these goals, we're really looking at reliably matching generation to load. And in the context of doing that, we're trying to keep the voltage within limits, the frequency within limits, and that's really the target. And it seems like a very simple thing to do, but if you imagine that this is a real-time machine, and we don't have really at this point in time cost-effective storage at any significant level, we now start saying it becomes a little bit more of a challenge. And we're used to historically having knobs to turn to match that generation to load, so it's a little different. So there's various levels of planning. I'm not going to spend a lot of time here. I would like to say that as you go at a higher level, you start to look at it from a system perspective. It's much bigger. The issues at system level are different than those at a distribution level, which are generally much more focused and much more localized. So I think from a utility perspective or from a end consumer perspective, this is something that I don't think people really quite understand, is that if you were to look at it here now, this is for SDG&E, if you look at a March peak day 2020, you can see here what these installed capacities of rooftop solar are, as well as central solar and wind, and what the net impact is on the actual load that the system experiences. And so you've got, those work so well. So you've got a couple of different things here that are going on. And see, here's the overall load, and here's the net with wind and solar. So I think the challenge here gets to be, and you think, well, that's really not that big of a deal, is it? And so you have these sort of these, what is called these, affectionately known as these duck curves. The California ISO has said by 2020 at the California ISO level that actually this little ramp right here that you're seeing is actually going to be 13,000 megawatts in an hour and a half. So for those of you that have some feel for what that means, a big, large combined cycle plant might be on the order of 600 megawatts. We're talking significant amounts of generation that has to ramp to meet these needs. You'll also note here, this is what would historically be our typical system peak. For those of you that look at what we try to do, we actually are planning for historically that little peak that you see up here. It's that 1 hour of the year, the hottest day of the year. That's what drives all the capital infrastructure investments in the utilities, whether that be generation, transmission lines, distribution lines. You can see here, obviously, the net now starts to push that peak out here to 7 or 8 o'clock at night. At that point in time, the ability of solar in particular, obviously, to impact what's occurring on the grid or impact system planning becomes very small, and that becomes part of the challenge is associated with how we as a utility actually manage the grid. So one of the things people say is, okay, well, what are the big challenges? Wind blows, the sun's there all the time, right? So this is from the California ISO, and this shows basically 1 month of wind production in California. Question is, which day do you want? Which day do you pick? So for those of you that haven't seen this kind of curve, you've got this nice average production, but any particular day doesn't look very good. So the real challenge, I think, for a utility is to say, obviously for renewables, one of the biggest deals is actually the ability to forecast. And more accurate forecasting is becoming more and more important as we move forward in time. And the use of that forecast data becomes really important. So the question really is, looking for a day ahead, looking for an hour ahead. These are actual real production curves. And so now when we talk about managing the load and generation balance, you have to make up for these fluctuations that occur. So here's now a large PV system. Okay, this is in desert in East County. This shows every single day of February. Okay, if we actually now sort of zoom in to right in here, what you've got, the blue is the actual power production. The pink here is the 69 kV bus voltages, and the up here are basically the 12 kV distribution bus voltages. But if we zoom in here, you can see very rapid changes in a 26 megawatt array, okay, out in the desert. You can see here, these are operational limits. And you'll see here that we are actually in violation of those operational limits. And we've got significant movement of our 12 kV bus. So this is a transmission interconnected system that moves the transmission system around here. And that movement on the transmission system actually impacts the distribution system. So it does create challenges as the penetration levels increase significantly. So I think one of the key here is what a difference a day makes. So this is the day immediately preceding. And you can see here, here's the actual production data, PV output. Here's the bus voltages, and here's the actual 12 kV bus voltages. In this particular case, this particular company actually has more panels than what you would historically size say a rooftop PV system on it. And therefore, they're basically able to flatline or compress and continue to put additional power out there. So this is SDG&E service story. So you're here sitting down right over, basically right in here. We have 4,100 square miles. We serve up into South Orange County. We have our eastern edge of the Sonora Desert here. For those of you that have traveled around San Diego a little bit, you'll notice here you got all the nice beaches. And then you move inland, you get the mesas. And then you go in and you start getting the coastal, sort of the ranges here in the mountains. And then ultimately going out into the desert. There's a couple of really interesting things here. At the end of July of this year, we had roughly 26,000 rooftop PV systems in San Diego County, or in our service territory, 190 megawatts AC. We also have about 5,600 electric vehicles in San Diego County as well. And of those, about 4,500 of those are actually true electric vehicles. And it turns out that actually we have, who would guess, 775 Tesla S, Model S's. Nice cars. Our VP has one, several people have one at work. But the challenge here is you've been outside, although this is not typical for San Diego. We generally don't get these types of monsoonal kinds of high temperature, high humidity events. But we do get significant marine layers called May, gray, June gloom. And so for most people along the coast, the systems were designed and the homes were designed absent air conditioning. So they basically have 100 amp service panels. And what's the significance of that? Well, for any of you who know what in this particular case, a Tesla S on a level 2 charger will take 10 kilowatts. Your AC on your house is roughly 3 to 4 kilowatts. Obviously, you buy a Tesla S and plug it in, significant load. And oh, by the way, if you've been along here, along the coast, and if you looked in the paper to see how much those houses cost, It's really kind of interesting. So you've got a lot of photovoltaics going up along the coast. You also have a lot of electric vehicles going in along the coast. People who are buying these electric vehicles actually have to upgrade their services because they cannot accommodate that electric vehicle. I think one of the issues here is the fact that we also have clustering. And we also have, what we found is that a third of all the EV owners actually also have photovoltaic systems. So it's a really interesting shift in adoption of technology in early adopters. And we're also seeing a number of customers with electric vehicles on the same transformer. And so from a utility perspective, adding that significant load is really quite a challenge. So a number of things that cause a utility like SDG&E to be concerned. The infrastructure along here wasn't built to accommodate the EVs or necessarily the PV systems. We're finding that historically we might have had, let's say along the coast, 20 customers per transformer. If you move inland here, what you'll find is that we'll actually be 8 to 10 customers per transformer. So it's a little different, a little more robust infrastructure. But interestingly, that May, gray, June gloom that I briefly mentioned actually moves all the way into these areas here. And it's pretty extensive. And so when you think of PV and you think of those nice clear days in San Diego, we got a lot of periods of time where those do cause us some challenges, very short periods of time. Here's just a graph and a curve. This further defines, you got the residential installations, commercial industrial installations, and this is the California Energy Commission forecast. We're currently at, end of July, 190 megawatts, so we'll likely exceed their, and this is their aggressive forecast. And the bigger challenge actually for a utility like us is when the PV output is high, and the load is not very large, or it doesn't have a lot of air conditioning on. So in April, May timeframe, around 1 o'clock in the afternoon, if you're oriented due south. And once we start seeing these kinds of penetration levels exceeding 30% on a particular circuit, we start to see problems associated with performance on that particular circuit. And I'll show you some slides. So here's an example of, in this particular case, it's a 1 megawatt PV array, okay? I want you to note that not only is it a 1 megawatt array, but here's the data at various time steps. You take that data, start averaging it. It's kind of interesting to note as you look at the time scales change, that what the power output is doing and how much that has changed. The reason that this is important for us as a utility, most people tell us, well, we don't see any problems, or do you see any problems? And the answer is the AMI systems we've deployed here in San Diego and in most places actually only read on an hourly basis. So if you're looking at an hourly basis, what you would have seen is a pretty flat curve, and you'd say, what problems? And the truth is, this actually does cause us significant problems. So here's the corresponding primary circuit voltage for this 1 megawatt array. These are nominal voltage here. You can see the upper range, the upper acceptable range. You can see that we're also well above that most of the time. And this is actually when the fog is burning off on an inland location. This little box here is blown up down here. So this is a 10-minute block. And this is 1 second data. And so what you see here is that this PV system goes from basically maximum output down to basically 0, back up to maximum output. And that time frame's on the order of a magnitude of a minute. Why should you care? Why is that important? It's important because we have equipment. Remember I said our goal is to keep the voltage within tolerances. We have equipment in place in the substation, out on the circuit, that we're actually trying to regulate this voltage. We're actually trying to make this a nice smooth curve. With this change in this PV system, we're actually moving that voltage around significantly, and our actual regulation equipment in and of itself is operating much more frequently. It tries to follow this and correct this curve over here, but by time, it's got a 45-second delay. By time it actually knows to move, the PV system's come back up, and now it has to move back into its regular state. And so you can imagine the additional operations and that you will see given this. And the challenge for a utility is just the fact that those additional operations really are driving additional costs and additional O&M for us, for the utility, where we would actually have to replace these voltage regulation equipment much earlier than we otherwise would have. So here's the challenges. Here's why for utility. You can see here we talk about being outside these operating ranges. One of the things, this non-CVR, CVR here is a program called conservation voltage reduction. People call these green circuits. People call lower the operating voltage at your meter such that you can now sit there and actually consume less energy. We have a program in California. We've had it since the late 70s. Roughly 70% of our load is CVR compliant today. What does that mean? Instead of a plus minus 5% range, we're now talking a 0 to minus 5% range. But as the penetration level of PV goes up, we're seeing our ability to maintain that voltage becoming much more difficult. SBEMA, Computer Business Equipment Manufacturers Association violations. So this is anybody who's got a PC or any sort of sensitive electronic equipment. Many excursions beyond limits on this particular circuit. And ultimately, we would expect in the long term, equipment's going to fail. And then we did talk about the O&M issues associated with doing and replacing equipment in 5 years versus 30 years. So this is an example of what we experience when we talk about a marine layer. And you talk about coastal eddies, the May Gray, June gloom in San Diego, for those of you that have stepped outside and see this kind of overcast. These are locations across the entire county. This is up in North Orange County here. This is about 60 miles. This is pushing in about 30 miles. So 60 miles here, 30 miles inland. People talk about diversity. They talk about the fact that if I have a PV system over here, then obviously this PV system over here is going to behave differently. Well, that's what we thought too. And then we did some measurements, and this is 15-minute data. And this is across the county. And I think you can see this is April 4th to 8th. And what you can see is that first day looks pretty good, second day not so great, third day even worse, fourth day worse yet. But it's consistent across the entire county. So from a utility perspective, not only is it a problem necessarily at a distribution level, but it will actually go up to the actual overall system or transmission level. And then when you sum them all up, you can see that if there was significant diversity, you would expect that these guys would be basically, they would have disappeared, but they haven't. So some additional challenges for us here in San Diego County. So just to try to say here as a utility, so I talked about here, these are our tolerances, plus minus 5%. If you're at CVR here, that's 0 to minus 5. CVR is 0 to minus 5. Here's the example. You got a big generator. That big generator comes in and actually pushes the voltage way up. And so what do you do? Well, what does that impact? What impacts that? So there's lots of things here. Location on the circuit is important, whether it's near the substation or at the end of the circuit. We've seen 100%, pretty much 100% loaded or PV loaded circuits or generated circuits where the ratio of PV to the load is 100%, but it's right at the substation on a very stiff feeder, and we haven't really seen a lot of problems at this point in time. What is the circuit rating, whether it's 4,000 volts or 12,000 volts? What type of circuit is it? Urban versus rural. Urban tends to be much shorter, much more intertie, much bigger conductors. Rural tend to be much longer circuits going various places. What's the minimum loading? If you got lots of load on the circuit, then the issues aren't as high or as bad necessarily as it would be if the loading was much lower. X to R ratio, so this is basically the ratio of the reactance to the resistance. Hopefully I'm not boring you all to tears, but aggregated DG capacity, and then what is the regulation from that? So there are solutions. We're looking at these solutions. Circuit modifications. People talk about demand response, but really much slower DPDT or rate of change of power events. 4-quadrant control devices. We'll show you a little bit about that. And then even a more interesting challenge is actually just really the regulatory and policy changes that are needed to occur to accommodate new equipment and some of the information. So here's an example of a solution and modeling solutions. Okay, so these are electrical models of that other circuit that you saw where you've got the PV system production varying significantly. In this case, all we're doing is injecting what we're calling is reactive power dynamically. And you can sort of see where this thing 4-quadrant comes in. You're operating in all 4 quadrants of this curve. Dynamic VAR device is just straight up and down on the reactive power curve. Energy storage without any 4-quadrant control is going to be just plus minus P. And you can see the net result after, which is the red curves, and you can see we're able to bring the voltage back within limits. And if you go to the 4-quadrant control with storage, you can see here how we've actually been able to pretty much flatline that voltage. And that's ultimately important as we think about the future and where we're going. So here's an example of a different kind, actual dynamic VAR device. And you know, some of these graphs must look like gobbledygook, I can imagine. Voltage is the blue. The real power is the orange. And the reactive power is actually the green. And this is a dynamic VAR device. So if we actually zoom into this little thing here, you can see here's with a dynamic VAR device on. These little pieces here. You can see really, really tight control of the voltage. We turn off that dynamic VAR device. You can see here we've turned it off. And you can see the significant change in voltage behavior. So we think not only things like energy storage, but things like dynamic VAR devices are also solutions. So I'm going to stop and be able to hopefully leave you some time for questions. I think the key point here is that when the grid was originally designed, that it was really looking at power flowing from large central station plants to the actual loads. The thought of reverse power flow was not something that was typically thought of. Economies of scale typically drove the large central station facilities. With the cost of PV, we know with the DOE Sunshot program, as the PV prices drop, we'll be seeing more and more distributed PV. So we're effectively seeing a doubling every couple of years, roughly, of the amount of PV on our system. So right now we have about 190 megawatts. In another couple of years, we'll probably be looking at 380 megawatts or 400 megawatts. The fact that both electric vehicles and photovoltaic systems do have a significant impact on the grid and how we actually have to manage the grid. That what historically we would have done to manage voltage fluctuations is inadequate as we move forward in time. And we also need new approaches as far as rate and rate design so that we can look at what happens in the future when in the state of California by 2020 all new residential homes are supposed to be net zero energy. What does that rate structure have to look like for a utility to actually be able to recover its costs of service? This little thing here, smart inverters. Well, it's really not smart. It's really just got additional functionality. It's really being able to do some things very differently than historically what an inverter has done, which is basically do the DC to AC conversion. But in order to do that, I mean, the real challenge here actually is we need to change rules. And I know most of you here probably don't really think much about regulatory and policy work. I unfortunately spend way too much time doing that. I can tell you to start any change, whether it be in Sacramento or at our Public Utilities Commission, from a start to finish is a 3 to 5 year timeline. So while you may say, it's easy, simple, go do it, that's not quite how it works. When you get regulators, legislatures, and policymakers involved, it takes a long time. So with that, and that's actually a nice clear sunny day. Thank you, and I'll be happy to take some questions for anybody who